Just trying to, okay, there we go. Okay, so in my talk today, I want to focus on what the Earth's atmosphere might have been like during the Archean period, imagined here in this artist rendering, and ask what JWST might be able to see if nearby exoplanets have similar atmospheres. So there's no doubt in my mind that JWST has the potential to revolutionize exoplanet atmosphere studies with a mirror that has roughly 7 times the collecting area, a stable L2 orbit to allow for continuous stare observations and a much broader wavelength coverage. JWST is obviously a major step up from Hubble, but will it be able to detect biosignatures? And that's a question I want to explore today. So specifically, what I'm going to present is some work that I've recently published in the paper that's listed here. So in this paper, I looked at the detectability of methane and carbon dioxide in the atmosphere of TRAPPIST-1e, because this pair of gases has been proposed as a biosignature, as I'll explain shortly. The main aim of this study was to determine if the methane carbon dioxide biosignature could at least in principle be detected with JWST. And I also wanted to investigate how the detectability of these gases might be affected by clouds or haze at different altitudes in the atmosphere. And so, as a bit of background, there have been other studies that have looked into this same question before, and in particular, my own study was directly inspired by the work of Christensen-Totten et al., who also investigated the detectability of methane and carbon dioxide in the atmosphere of TRAPPIST-1e. But there are a few things that set my work apart from the Christensen-Totten study. So for one thing, I used the latest system parameters for TRAPPIST-1e that were recently published by Agol et al., which result in a somewhat lower surface gravity for TRAPPIST-1e, which means a stronger transmission signal for the atmosphere. And I also performed a more systematic investigation of the impact of clouds and hazes compared to Christensen-Totten. And I also made use of a Bayesian evidence framework for evaluating the detection significance of methane and carbon dioxide in the atmosphere. So before looking into anything else, if we're going to use JWST to conduct a biosignature search, what would be the best target to pick? Is it TRAPPIST-1e? So for any biosignature search that we'd want to conduct, would probably have to do that using transmission spectroscopy, or I think certainly would have to do that using transmission spectroscopy, detecting the thermal emission of a 300 Kelvin Earth-size planet will require precisions greatly exceeding what JWST should be able to achieve. Then in terms of the best transmission spectroscopy targets, basically, we'd want a transiting planet with an unambiguously rocky composition orbiting a nearby, preferably small star. Since the measurement will be extremely challenging to make, it's important to carefully consider the list of possible targets carefully. So let's look at TRAPPIST-1e within a broader context. So here is a plot of rocky planets that transit with the insolation that they receive along the horizontal axis and their radii along the vertical axis. Currently known planets with published mass measurements are labeled on this plot, and all of the other planets that are shown are hypothetical planets that are expected to be found by tests based on the predicted yields of Barclay et al. So each planet is color-coded by its host star spectral type, and it's clear that most of the transiting rocky planets will be around red dwarfs, largely thanks to the small stellar radii, making them easier to detect. And if we take into account the properties of each system that is plotted here, and rescale the marker sizes according to how good those planets are for transmission spectroscopy, then this is what we see. And the TRAPPIST-1 planets really stand out as some of the larger circles on this plot, meaning that they're among the most favorable, which I'm sure many of us already know. And this includes, though, them being the most favorable, including those planets that TESS is predicted to find. So if we also overlay the rough habitable zone with the more conservative range shown in dark green and an optimistic range in lighter green, then there really is only a small handful of possible targets to consider. And of these, 3 of the TRAPPIST-1 planets, E, F, and G, fall within the conservative habitable zone. But 3D climate models, such as those run by Turbay et al., suggest that planets F and G would require a substantial quantity of greenhouse gases to maintain habitability, whereas the habitability of TRAPPIST-1e is more stable for a wider range of atmospheric assumptions. So for these reasons, the predicted strength of the atmospheric transmission signal and the robustness of the atmosphere's habitability, these make TRAPPIST-1e really the standout target that we have for a biosignature search. And it really is worth stressing that we don't necessarily expect TESS to find any better targets. Just remembering that the unlabeled points here are planets that TESS is predicted to find based on well understood statistics of short period planets from Kepler. So I'm possibly a bit out of date on this, but to my knowledge, TESS has only discovered 1 habitable zone rocky planet so far, TOI 700d. It's not actually plotted here because I don't think it has a published mass measurement yet, which is a prerequisite for transmission spectroscopy. And another caveat to note is that predicted discoveries by the Speculus survey, which is targeting very late M dwarfs, aren't shown, partly because the occurrence rates for planets around late M dwarfs aren't very well understood. But in any case, there haven't been any Speculus discoveries published yet, so it's not clear how or if they're going to affect this plot very much. And the bottom line is that for now, TRAPPIST-1e really is the best target that we have and possibly ever will have for conducting a biosignature search using transmission spectroscopy. So what do we currently know about the atmosphere of TRAPPIST-1e? Although the TRAPPIST planets have been observed with HST, we're still more or less completely ignorant about their atmospheric composition, and that's summarized in this figure here, which shows measured transmission spectra for planets D to G. And essentially all of the data are consistent with flat lines at the measurement uncertainties. And yeah, the precision is just nowhere near high enough to determine if this lack of observed spectral features is attributable to a high mean molecular weight atmosphere or clouds, or perhaps even a lack of atmosphere. All we can do right now is rule out, based on these data, scenarios in which the atmospheres are hydrogen dominated and free of clouds, basically, which we would have considered highly unlikely in the first place. Okay, so I'll come back to TRAPPIST-1, but now let's just take a quick look at the Earth's infrared transmission spectrum, shown here based on real measurements that were made by a satellite in low Earth orbit. And we see in this spectrum 2 of the most prominent gases that together are considered a biosignature, oxygen in the form of ozone and methane. If both of these gases could be detected together in the spectrum of an exoplanet, it would be a strong indicator of a biosphere that's producing methane and oxygen as metabolic byproducts. JWST has spectrographs that cover the entire wavelength range shown here, but in practice will probably be limited to shortwoods of about 11 micron for spectroscopy. That may or may not turn out to be the case, depending on how the IFS longer wavelengths performs. But this range, shortwood of 11 microns, still includes ozone and methane bands. And so since we don't have any constraints on the atmospheric composition of TRAPPIST-1e right now, we're still free to speculate. So we can ask the question, if TRAPPIST-1e does have an atmosphere similar to the modern Earth's, what might we be able to see? And here's a figure from the Origins final report that shows what JWST could potentially measure if TRAPPIST-1e has a modern Earth-like atmosphere and we were to observe 60 transits. And so observations made with near spec between 3 and 5 micron are shown in yellow, and those with MIRI between about 5 and 10 micron are shown in green. And the key point is that even with such an ambitious web program of about 250 hours devoted to a single exceptionally favorable target in TRAPPIST-1e, then the strong ozone band at 10 micron is undetectable, which is pretty obvious by eye. So I think there's fairly broad consensus that Webb won't allow us to detect a biosphere resembling the modern Earth during its lifetime. But to be clear, like, there are other strong features that, as we'll see, are potentially detectable in temperate rocky planet atmospheres. But for the specific case of oxygen, it seems really hard, probably impossible. But I do want to note this 2020 paper by Thomas Fachet, which drew attention to a previously overlooked collision-induced absorption band caused by oxygen at a wavelength of around 6.4 micron. And this does fall within the MIRI LRS bandpass, but it's not as strong as the ozone band at around 9 microns. However, MIRI is less noisy at these shorter wavelengths, and the band is quite broad, which potentially helps with detectability. So here is a plot from the same paper that shows the number of JWST transits required for a 5 sigma detection of O2 as a function of the distance to the planetary system, while assuming that the other properties of the planet are the same as TRAPPIST-1e. So the black line shows the results for a 5 sigma detection of the 6.4 micron new or previously overlooked band, while the dashed blue and dotted red lines show the results for other O2 bands at shorter wavelengths. And so the 6.4 micron band is about 10 times easier to detect than the shorter wavelength bands, but even so, because the distance to TRAPPIST-1e is about 12 parsecs, a 5 sigma detection of that band would still require about 800 transit observations, which is not realistic. So if a TRAPPIST-1e analog could be discovered much closer at around 4 parsecs or closer, then we're starting to get below 100 transits that's required, which is maybe starting to come within the realms of possibility. But it's a big if, because we already saw that none of the predicted habitable zone test planets are expected to be more favorable than TRAPPIST-1e, and the yield of planets from Speculus is currently a big unknown. So overall, I personally think the prospects of using JWST to detect oxygen in a habitable rocky planet's atmosphere are really remote. But oxygen isn't the only biomarker to consider. So evidence for life on Earth dates back to around 4 billion years ago. And since then, the atmospheric composition has evolved significantly, with the biosphere playing a key role in this evolution. And so in very broad brushstrokes, during the Archean eon, carbon dioxide levels were relatively high, along with methane, thanks to methanogenic bacteria. And then during the Proterozoic, carbon dioxide levels started dropping thanks to weathering by growing continental crusts, and bacteria also developed photosynthesis, which started to raise the oxygen levels. Meanwhile, the oxygen in the atmosphere likely was reacting with methane, lowering the methane abundance. And then following the Cambrian explosion about 500 million years ago, we eventually end up with the modern Earth's atmospheric composition with significant concentrations of both oxygen and methane maintained by the biosphere. So here's a diagram that summarizes how the prominence of biologically relevant gases have varied over this time along the horizontal axis, divided between those that would have been least detectable in the lower half of the panel and those that were more detectable in the upper half. So basically, methane would have been good during the Archean, and oxygen would be good in the last 500 million years. Turning back to JWST, you'll recall, though, that oxygen seems to be out of the question. So that leaves us with methane. But methane on its own could be ambiguous because abiotic processes can generate methane, or for whatever reason, the initial volatile content of the planet could favor high methane abundances. But in 2018, Christensen et al. Published this paper proposing that the simultaneous detection of methane and carbon dioxide could be a more promising biosignature. So this is outside my area of expertise, but this slide illustrates why the combination of methane and carbon dioxide is a promising biosignature. So according to this paper, if the atmosphere and ocean were left alone to reach chemical equilibrium, then the reaction shown up the top here would result in the carbon dioxide, methane, and nitrogen reacting with water to form the ions that are shown on the right-hand side, which would dissolve in the ocean. So apparently this reaction would reduce the methane abundance by about a factor of 100. And that's illustrated down the bottom in the bar diagram, with blue bars indicating the abundances of various gases during the Archean, and green bars showing the corresponding equilibrium abundances. So, as I said, for methane, the abundance was about 100 times higher during the Archean than we would have expected if the atmosphere was in chemical equilibrium. So a methane abundance of greater than about 1 part per thousand, along with a detection of carbon dioxide and conditions suitable for a liquid water ocean, would be very suggestive of an Archean-like biosphere. So the higher the methane abundance, the higher the likelihood of a biological origin. Okay, so although there are abiotic sources of methane on the Earth, for instance, they're dwarfed by biogenic sources. And this is a plot from a paper by Thompson et al. That summarizes the estimated ranges of abiotic methane fluxes with a log x-axis in units of teramoles per year. And then the little blue bar in the top right, it shows the biogenic methane flux of the modern Earth, which would have been even higher during the Archean. So even if you took the extreme upper ranges of all the abiotic sources and added them together, then the resulting methane flux would be less than that of the biogenic sources. And this is why a detection of methane with a sufficiently high abundance, along with carbon dioxide and the possibility of a water ocean, would be a strong indication of an Archean biosphere. Okay, so let's have a closer look now at some transmission spectrum models across the wavelength ranges covered by JWST's instruments. So this is a model, now it's not a measured spectrum like the satellite one I showed before, of the modern Earth's transmission spectrum from the optical through the infrared. And here are the wavelength ranges covered by Webb spectrographs. So aside from ozone at 10 micron, the carbon dioxide band at 4.3 micron is a particularly strong feature that we see. And here's what we think the Earth's transmission spectrum might have looked like during the Archean eon. So the oxygen is missing, but carbon dioxide remains strong. And the high methane abundances result in multiple absorption bands that are within the nearest and near-spec ranges. And what's more, near-spec has the dispersive prism that can cover the full 1 to 5 micron wavelength range in a single shot. So with a single transit observation, the near-spec prism would cover the strongest carbon dioxide bands and multiple methane bands. So perhaps it could be used to efficiently search for the biosignature pair of carbon dioxide and methane. And the Christensen-Totten et al. Study actually investigated this possibility in a follow-up to their original paper, where they proposed this carbon dioxide methane Archean biosignature pair. And so for their target, they also selected TRAPPIST-1e. And here the black line shows a model transmission spectrum, assuming an Archean-like composition, the same as, or very similar to at least the one that I showed on the previous slide. And the red bars show a synthetic data set comprised of 10 transits co-added together to beat down the noise. So a mock analysis, a retrieval analysis performed on these data was then able to show that the carbon dioxide and methane abundances could in principle be constrained to within about an order of magnitude of the input values, which are indicated on the right here by the blue lines. And so from this, the authors concluded that an Archean-like biosphere could be potentially identified for TRAPPIST-1e with 10 transits observed using the near-spec prism. And that corresponds to a fairly modest observing program of 40 to 50 hours. So I was initially surprised and skeptical that it would only take around 10 transits to measure spectral features in the atmosphere of a temperate rocky planet with a high mean molecular weight atmosphere. Because as an observer, I've had quite a bit of firsthand experience acquiring data and it being trickier than you initially may have thought to deal with in practice, compared to what the case might have been on paper with hypothetical instrument noise and models of the atmosphere. So for example, here's a transmission spectrum that we measured for the 500 Kelvin sub-Neptune HD 3167c. And so in fact, this is one of the most precise transmission spectra that's ever been measured with HST, with a median uncertainty in each of these wavelength channels of around 15 parts per million. But even in this case, we were only able to make a tentative 2.5 sigma detection of molecular absorption, and we weren't able to unambiguously identify the absorbing species. So right now with Hubble, we're currently struggling to detect atmospheric features in the transmission spectra of gas-rich sub-Neptunes in general. And is JWST really going to be such a leap forward that we can start characterizing temperate Earth-like planets? So to consider this a bit more quantitatively, if we assume that HD 3167c has a hydrogen-dominated atmosphere with a heavy element enrichment of about 100 times solar, then that would mean a mean molecular weight of 4 atomic mass units. And then using this, along with the planetary radius and mass and the stellar radius, we can calculate the change in transit depth due to a change in one pressure scale height of the atmosphere. And that comes out to be about 10 parts per million. So if we go through the same calculation for TRAPPIST-1e, but assume that the atmosphere is nitrogen dominated with a mean molecular mass of around 29 atomic mass units, then that would give a change in the transit depth corresponding to a pressure scale height of around 15 ppm. So here TRAPPIST-1e is really helped by the fact that it orbits such a small host star, which results in a larger transmission signal. But if we also account for the difference in brightness between the two host stars, HD 3167 has a K-band magnitude of around 7, whereas TRAPPIST-1 is fainter than 10th magnitude in K. Given that, the actual signal to noise of HD 3167C observations on paper should be around 3 times higher than for equivalent TRAPPIST-1 observations. And remember that on the previous slide, I was showing that we're really struggling to detect spectral features in the atmosphere of HD 3167C with 5 co-added HST transits. Okay, but JWST will have a bigger mirror, right? And yes, that is going to obviously boost the signal to noise, but how dramatically will it do so? So let's compare the hypothetical measurement precision of HST and JWST. So here's a figure showing wavelength along the horizontal axis against the noise in the measured transmission spectrum per resolution element along the vertical axis, where I'm assuming a spectral resolving power of 80, which is what the Hubble transmission spectrum I showed previously was at. So these purple points show the expected noise for a transmission spectrum of TRAPPIST-1e measured using wide field camera 3 on HST. And then if we then reduce this noise by assuming that it just bins down as the square root of the number of photons that we collect, then we can simply multiply these values by the ratio of HSTs and JWSTs mirror diameters, and this is what we'd get. So that's a pretty naive calculation. What do we actually expect the instrument noise to be for near-spec prism observing a TRAPPIST-1e transit? And that's what this orange line is showing here. So bin to the same spectral resolving power. Per resolution element, the noise isn't reduced by as much as a naive scaling by the mirror diameter might lead us to believe from the HST precisions. But the real value of JWST, in my view, will be the fact that the light that we receive will be spread out across a much broader wavelength range and giving access to many more spectral features than we've had access to previously. So given that JWST's noise won't necessarily be a factor of 3 lower than HST over an equivalent wavelength range, and given that we're already struggling to detect spectral features on sub-Neptunes that should be 3 times easier with HST compared to TRAPPIST-1e, then this means that it's going to have to be the extended wavelength range of JWST that does the heavy lifting if we're going to have a hope of detecting spectral features in temperate terrestrial atmospheres. So my belief is that like JWST won't necessarily be a miracle machine, and the challenges that I've experienced personally with HST data previously were a large part of the motivation for independently evaluating the claim that spectral features could be detectable in the atmosphere of TRAPPIST-1e with JWST. And another effect that I wanted to investigate more closely was how problematic aerosols in the atmosphere might be. So clouds and haze, as many of you I'm sure know, have had a really big impact on our ability to measure spectral features with HST. So for example, here's our transmission spectrum again for HD 3167C, shown on the left, along with models that were obtained from a retrieval analysis that included clouds. And then on the right is the posterior distribution for the cloud top pressure versus the atmospheric metallicity, showing this classic degeneracy between these two properties that prevents us from constraining the chemical abundances very precisely. So in my paper, I investigated the detectability of methane and carbon dioxide with a more systematic focus on how clouds and haze in the atmosphere might affect the results. So on a temperate planet, we might expect water clouds to form. On Earth, water clouds typically only extend to around 6 kilometers in altitude, but general circulation models suggest that water clouds could extend higher, above 10 kilometers in altitude in the atmospheres of tidally locked planets like TRAPPIST-1e. And if the atmosphere is methane rich, like in the Archean scenario, there's the possibility that photochemical haze could be forming at even higher altitudes. So for an Archean-like atmosphere, photochemical hazes similar to those of Titan's atmosphere could form, greatly suppressing the amplitude of spectral features in the transmission spectrum, like what we see here for a real observation of Titan's transmission spectrum measured with Cassini, where the photochemical haze is greatly reducing the amplitude of the methane absorption bands. And models of TRAPPIST-1e's atmosphere also suggest that photochemical haze could indeed form. So here are some model transmission spectra for TRAPPIST-1e, assuming an Archean atmosphere from Thomas Fauchet's work. So the green and red lines show 2 cases that include photochemical haze, which extends from, in terms of opacity, about 1 millibar in pressure at the shortest wavelengths to about 100 millibar at longer wavelengths. So when compared against the other models that are shown here that don't have haze, it's very obvious how strongly it can affect the transmission spectrum and reduce the amplitude of spectral features. Okay, so here onto my work. Here's the baseline transmission spectrum that I adopted for TRAPPIST-1e over the 1 to 5 micron wavelength range covered by near-spec prism. So it assumes an Archean-like composition with 5% carbon dioxide, 0.5% methane, trace amounts of carbon monoxide, and the rest nitrogen. This is just basically the same composition that Christens and Totten adopted in their paper. So highlighted in pink are the strongest methane bands, and carbon dioxide features are also highlighted. So in addition to this baseline clear atmosphere model, I considered 8 different cloudy/hazy cases where the cloud /haze, I'll just use the term cloud from now on, was simply treated as a wavelength uniform opacity source across a range of pressure levels between 600 millibar and 1 millibar. So that is a simplification because, as we saw in the models before, the haze can have quite a strong wavelength dependence, but this is just a fairly simple analysis of the effect of cloud at different pressure levels. Okay, so here is the 100 millibar cloudy case, and you can see how the spectral feature amplitudes are reduced. And then here is the 10 millibar cloudy case. And as I was saying, I also considered a range of other cloud top pressures that aren't actually plotted here. So very crudely speaking, you can perhaps think of the clear case as maybe being like a dry planet scenario, and the 100 millibar case as a planet with an ocean, a water-rich planet, where the opacity at 100 millibar is due to water clouds. And then the 10 millibar case might be something a bit like a Titan-like hazy atmosphere scenario. But to emphasize, I've made no assumptions about the cloud or haze compositions. And in reality, it's worth stressing just how the aerosol opacities will often have that wavelength dependence, such as the slope that we saw on the previous slide from the physically motivated models. So to produce mock JWST datasets, I used the Pandexo software. And an important point was that I implemented a partial saturation observing strategy, which was proposed in 2018 by Battaglia et al. And the basic idea of this observing strategy is to allow some of the pixels on the detector to saturate. in order to achieve longer exposure times and hence higher observational efficiency. And so for those pixels that do saturate, they're not completely wasted because the earlier detector reads before they reach saturation can still be used to recover the fluxes at those wavelengths, just with a lower duty cycle compared to the pixels that don't saturate. So in the end, as you can see here, this greatly improves the overall measurement precision that we should be able to achieve with the partial saturation strategy shown in green, and then the non-saturation equivalent shown in pink. Okay, so here is a mock data set generated from the clear atmosphere model shown in orange here, and assuming just a single transit observation of TRAPPIST-1e. So obviously we wouldn't be able to detect anything at this level of precision, but if we were to co-add 10 transits, then the precision will greatly improve, obviously, to a point where we're actually able to maybe start tracing out some spectral features. And so here's what that same data set would look like with 10 co-added transits just zoomed in, where we've assumed that the measurement noise is binning down optimally as Poisson noise according to square root n. So these are the kinds of mock data sets that I performed my mock retrieval analyses on. So specifically, I ran retrieval analyses on these sorts of synthetic data sets, fitting for the atmospheric properties such as an isothermal temperature profile, abundances for different chemical species, and cloud top pressure. And for each cloud top pressure scenario, I did this ranging from the clear atmosphere to a cloud deck at a millibar, and this was repeated for a range of co-added transits going from a single transit observation through to 50 co-added transits. Okay, so in terms of the Bayesian framework, for each of these retrievals that was performed, to actually determine if we actually detect methane or carbon dioxide and the confidence with which it's detected, I adopted the strategy that's outlined here. So specifically, nested sampling was used for the model fitting, along with or allowing the Bayesian evidence to be computed for each model. And to start with, this was done for a model that included a suite of plausible gases that may be spectrally active in the atmosphere. And then this analysis was repeated for models with carbon dioxide and methane removed one at a time. And by comparing the Bayesian evidence for the full model to each of these models with one gas removed, we can then quantify how confident we are that we need that particular gas to explain the data. This is fairly straightforward Bayesian model comparison. I believe it was Benecke and Seeger who first proposed this particular approach for interpreting exoplanet atmosphere data, and it's been used in various other studies recently, such as the ones listed here. And I think it's especially well suited to identifying biosignatures where we want to unambiguously identify very specific gases and not get fooled by false positives. And here's the summary of the results for carbon dioxide detections. So the number of co-added transits is shown along the horizontal axis, and the detection significance in terms of n sigma is shown along the vertical axis. The colored lines show the results for each of the different cloud assumptions, and then just above the axis, I've indicated the different classes of JWST program that each of these number of transits would fall under. So in short, for cloud at 50 millibar pressures or higher, so the pink line and leftwards, and down to a clear atmosphere, 5 sigma detections would be possible within the scope of a medium program of 60 transits or fewer. However, we'd need a large program of more than 100 transits if there's cloud at 10 millibar or 5 millibar, whereas a cloud or haze layer at 1 millibar would prevent the detection of carbon dioxide, even if we co-added 200 transits. And the story is quite similar for methane, which is shown here. So again, medium programs could, in principle, give detections of methane if cloud and haze is restricted to pressures of 50 millibar or higher, while a large program would be needed if there's cloud or haze at 10 millibar. So for cloud or haze at lower pressures, 5 sigma detections, again, wouldn't be possible for under 200 transit observations. So checking what some of these data sets might conceivably look like, here's a 10 transit observation for a clear atmosphere scenario. And here is the same thing for a cloud layer at 100 millibar. So according to this Bayesian framework that was used to determine the detection confidences, for this data set, the carbon dioxide and methane detections would both be at the 5 sigma level. And this surprised me at first because the signal to noise for any individual spectral band doesn't appear to be very high. But when the information contained across the full wavelength range is factored in, the detections become significant. Then in terms of constraints on atmospheric properties, here are the posterior distributions for, in this case, a clear atmosphere and 10 co-added transits. And the main thing I want to note is that we could conceivably constrain the methane and carbon dioxide abundances to well within a dex if we have these 10 co-added transits. So I also want to go back to this plot and consider the detection of methane for the 10 millibar cloud scenario shown by the dashed brown line. So a 5 sigma detection would require about 30 co-added transits in this case. What sort of precision does this correspond to on the transmission spectrum, and is it realistic? That's the sort of question as an observer I am interested in. Is the assumption of 30 co-added transits with 1/√n noise binning translate to measurement precisions that are realistic or unrealistically optimistic? So to check this, I plotted up the measurement precision as a function of wavelength for different numbers of co-added transits, similar to the plot I showed previously illustrating the effect of partial saturation. So the pink line is 10 co-added transits, the green is 20, and the blue line is 30 co-added transits. And the gray shaded region shows the measurement precisions that have already been demonstrated by HST's wide-field camera 3, which uses fairly similar detector technology to near-spec. And the key point is that for the assumption of 30 co-added transits, we're talking about measurement precisions that have already been demonstrated with wide-field camera 3. So it seems plausible that a 30 transit program really could reach this level potentially. And then here's just a plot showing what the transmission spectrum for a 30 co-added transit program might look like. But I won't dwell on that. I think I'm pretty close to the end. And here in this slide, I wanted to highlight that in terms of what's planned for JWST cycle 1, is that one of the GTO programs will be observing 4 transits of TRAPPIST-1e with near-spec prism, employing the partial saturation strategy. And so reading off this figure, if TRAPPIST-1e has an Archean-like atmosphere, that's a very specific assumption, of course, then 4 transits might be enough to give 3 sigma detections of methane for cloud down to pressures as low as about 100 millibar, so roughly where the tops of water clouds might be predicted based on circulation models. But if there's cloud or haze at lower pressures, then we basically won't see anything with just the 4 transits. And this is what the data for a 4 transit program might look like. And perhaps you can convince yourself that you're starting to see some of the spectral features, at least at the short wavelength end for methane. But I feel that a 10 transit program is probably the minimum we'd really need to start seeing spectral features at reasonable confidence if there's cloud at 100 millibar, which is where models do predict water cloud to reach up to for planets like TRAPPIST-1e. So fortunately, of course, it looks like JWST's mission lifetime is going to be significantly longer than the nominal 5 years. So let's hope that we'll be able to get more than the 4 transits for TRAPPIST-1e that are planned in cycle 1 in subsequent cycles. Okay, so with that, I'll conclude. So in summary, it looks like oxygen at modern Earth levels is unlikely to be detectable with JWST, even for the most favorable target that we know of, TRAPPIST-1e. Whereas methane and carbon dioxide are potentially detectable for TRAPPIST-1e under the very specific assumption that it has an Archean-like atmosphere. For cloud and haze at pressures down to 100 millibar, then 5 sigma detections of both of these gases might be possible with 5 to 10 transit observations, which is really quite a modest observing program. But if there is cloud or haze at around 10 millibar, which is where photochemical haze might start becoming significant, then 5 sigma detections of both these gases would require more like 30 transit observations. Whereas if you've got cloud or haze at 1 millibar pressures, then it's probably going to, almost certainly going to prevent the detection of either gas for any reasonable observing program. And yeah, with that, I'll conclude, and thanks for listening, and I'm happy to take any questions.
Awesome talk, Tom. That's super interesting. Thank you very much. Do we have any questions? I see that we have 2 comments in the chat. The first one by Emily Gilbert. So we are working on getting you the mass for TOI 700D. Yeah, that's right. So soon.
Great.
And from Mike Way. So can you get that much methane in a dry planet case?
I don't see why not. Do you have any specific reason why you don't think it would be likely?
Well, how do you produce it? That's the question. I mean, if you're going to have serpentization, you need water. And if you don't have water, you can't create CH4.
Yeah,
so
okay.
I don't see, and we don't see, I mean, most of us don't believe there's methane on Mars.
Right.
So if you don't see methane there, I think that's kind of a barometer of what we're talking about.
Okay, so yeah, this is well outside my area of expertise, but the methane abundances I was assuming were just simply rough estimates for what the Earth's Archean methane abundance was based on biogenic fluxes.
Right. But Earth wasn't a dry planet. That's all I'm saying. It's cool.
Right. Yeah. Okay. So that sort of comment about the categories being dry planet, water planet, and a Titan-like planet were very, very loose statements.
No worries.
Yeah.
Thanks.
Thank you, Mike. Okay, so we have a question from Vlad first.
Yes, hello. Thank you very much for a nice talk. I just have a question about your assumption of 1 bar atmosphere. So the point is that recent observations of TRAPPIST star, X-ray observations, and extreme UV emission reconstruction by Wilson, it's the MUSCLES program, you know, the Hubble Space Telescope program, suggest, you know, very high extreme UV fluxes, even from a star being so old, you know, 7 billion year old. And so our team have conducted the atmospheric escape calculations for the fluxes that they provided for the outermost planet for TRAPPIST-H. It's at 30 times the XEV flux from the current sun. And for E, it's already 100, meaning that we found that if the XEV flux is greater than 60, then the planet still undergoes hydrodynamic escape. So which suggests that, it should have, might be very low atmospheric pressure or none. So that's just, unfortunate conclusion that we have from such an active star. It's even old, but still active, so.
Yeah, I wouldn't challenge that in any way. Like I said, this was an exercise with very, very specific assumptions. If it happened that TRAPPIST-1e has a 1-bar Archean-like atmosphere, would we have a hope of detecting anything, and how many co-added transits would we need to see that? I got to say, I think if those assumptions actually held, we would hit the jackpot. It would be virtually miraculous if that's actually what the reality is. But looking at the numbers of co-added transits that are required to make such a detection, if those assumptions held, it doesn't seem too crazy, and maybe not necessarily a waste of telescope time, especially given the fact that there are other atmospheric compositions that may be detectable besides the very specific single composition that I've assumed here. I totally take your point, though. I think there's a good chance that TRAPPIST-1e doesn't have much of an atmosphere, but it'd be great to look.
Yeah, so we have other exoplanetary systems like TOI 700 that is well worth to be considered, because let's say, the XEV flux is only about 10 times of the current. So the number of systems are much, much better to be considered for JWST. That's what I'm saying. Thank you. Yeah,
good point.
Yeah, but TOI 700 is like 100 light years away, so the noise will be really bad, and the star is much larger, and so the transit depth will be way smaller. So that's the problem as well. We are going to have transit depth that are below what we expect for the noise floor of near-spec prism. So it will be extremely challenging as well.
That's a good point. I mean, that's kind of what I was trying to explore with those plots I showed at the beginning with planet radius versus insolation, and looking at which planets actually do fall in the habitable zone and have decent transmission spectroscopy signal to noise potentially. And yeah, it looks like TRAPPIST-1 really stands out. And we may not find a better target unless Speculus starts producing some really great TRAPPIST-1-like analogs.
Yeah, ideally we want a TRAPPIST-1-like system, but closer than 12 parsec would be really great. But yeah, so far it's not the case. Avi?
Hey, Tom, really great talk. Wonderful paper. Really love the work. I'm actually going to recommend this talk to any students or postdocs kind of jumping into this, this question of what can be detected with what. One thing I wanted to bring up that you have a lot of experience with is this problem of the uncertainty bars on each spectral channel not necessarily capturing the scatter apart from the models, essentially, where the models don't fit the data in certain cases within the uncertainty expected from the, the derived uncertainty from the data. And that really becomes challenging when you're trying to detect marginal detections of molecules or break degeneracies or things like this. My only question to you is, since you went through this wonderful sort of exercise of trying to estimate, how well we could detect something, have you thought through the ways that we could maybe capture that kind of outlier problem? Or I'm not quite sure how to sort of describe it, but that problem where the data, scattering the data or portions of the spectrum far, are far larger compared to models than expected.
Yeah, no, I don't have any special ideas about how to deal with that, but I do completely acknowledge that it could really be what ends up limiting us in this sort of observation. Often these things look beautiful on paper, and you're excited to get your data, but then when you see it, it's not quite as clear cut as you'd hoped. And that could well happen in this case. Maybe the one reason I'm a bit optimistic, though, if there was to be a larger multi-transit program of a planet like TRAPPIST-1e, is based on that plot I showed with the 30 transit co-adding of noise, like the precision that it ends up reaching is quite, I don't know, seems quite plausible based on our experience with HST, where we have binned multiple transits down to similar precisions, and like in a few cases it has been quite well behaved, that noise, and followed, or at least the pattern that we see in the data can be explained by quite plausible models. Yeah, I don't have a special cure or anything. If the systematics are worse than we might hope them to be, but like I'm kind of optimistic that JWST will, perform quite nicely, I suppose, to within some reasonable limit. Like 30 co-added transits, that's a lot, but yeah, maybe we won't quite achieve 1/√n binning down for 30 transits, but yeah.
No, it's a great point. I agree with you that multiple visits often, as you say, average out noise or systematics or other challenges. It's just with such a large wavelength range and number of data points that you're trying to leverage, with just some outliers or a portion of the spectrum that doesn't necessarily behave as expected.
Yep. I completely agree with you, Avi, actually.
Anyway.
I mean, I actually was very skeptical of this Christensen-Todden paper originally, that even on paper this could be done. So I was kind of just setting out to check myself whether or not it could be done, and to look at the effect of clouds more. So I wasn't able to prove on paper that it can't be done, but you can't really test the unknown systematics, and I suspect that they will complicate things much further than what we've been able to explore in this kind of lab exercise.
Great, thanks. Great work, though.
Thank you, Avi. Very nice.
So Tom, have you compared your retrieval method with another method like for TIE, for instance? We actually get twice as much transit than you predict. And what we do, we compute the full spectrum, we compute the spectrum without CO2, we do the difference between the two, and we compute the SNR across the whole band to get the CO2 SNR. And yeah, we have a transit that are twice as much than you predict. So have you made the comparison like that, and on the sensitivity of the technique?
Yeah, I don't know if I guess we're running a bit over. I could try to explain, like I've also wondered about this, and if you're interested, I can show some kind of toy tests that I've done where I think that it seems to me that if you do this Bayesian approach, then you can achieve higher detection significance like quicker when you're reducing your measurement uncertainty compared to, so you require fewer transits to reach a certain detection significance, because I don't know the mathematical reason why, but the whole Bayesian approach is maybe doing a better job of recognizing structure in the data, whereas like in this example I've plotted here, just a sinusoidal type signal. Let's say that's our data, and this horizontal line is the null hypothesis that in a frequentist framework you would be trying to rule out in the first place. Then over here on the right is along the horizontal axis is the size of the measurement uncertainty. So I'm repeating this experiment for different measurement uncertainties and calculating the p-value for the frequentist approach, and then the detection significance, which is plotted along the vertical axis. And you can see that the frequentist approach takes a long time. Like you've got to reduce the measurement uncertainties by quite a lot before the detection significance really starts shooting up. And I think that's because if you've got like a signal, like a sinusoid here, if you're not taking into account the ordering of these data points, then it could effectively look like random noise, just taken as a data set without any consideration of the ordering. But I guess the difference in the Bayesian approach is that you're comparing two hypotheses directly. So you're effectively comparing the sinusoid model here to the ability of the flat line to explain the data. Whereas in the frequentist approach, you're just comparing the data to the flat line. I don't know, but I also wondered about exactly what you're saying, which is why I did this test. And I don't understand the exact reason why, but for some reason, the Bayesian approach is picking up on the signal quicker than the frequentist approach, which I think you would effectively be using.
Yeah,
I don't know if that made any sense.
No, absolutely. I think I get that. But yeah, it would be very interesting to continue to talk about this later with you if you want, because I think, yeah, it's very cool.
Yeah, I need someone with more statistical knowledge, mathematical knowledge to help me understand, I think, but it's what my experiments have shown.
Yeah, no, that's very, very cool. Okay, well, yeah, we're running out of time now. Again, thank you very much, Tom, for your super interesting talk. It's really a great work, and yeah, looking forward to collaborate with you on that. I agree also with you, TRAPPIST-1e is definitely the best planet so far. And yeah, the next exoplanet seminar will be in 2 weeks, and so we will see you there. Thank you very much again. Bye.
Thank you. Bye.